Hello, this is Jeremy, and in this video I'm going to talk about how to find a probability distribution given a probability experiment. And so in this particular experiment we're told we have 3 defective motherboards in a package of 10. We're going to pick 2 motherboards without replacement, and our random variable is counting the number of defective motherboards. So the first thing I notice is that our random variable is counting, and so it must be discrete. In fact, if we're picking 2, then the number of defective could be none of them, right? Or 1 of them, or 2 of them. Even though there's 3 in the pack, we're only picking 2, so the most we could get are 2 defective motherboards. And so a probability distribution is going to be essentially a table, because this is discrete, of values of x and their corresponding probabilities. So what I need to really do is find the probability x equals 0, the probability x equals 1, and the probability x equals 2. Well, the probability x equals 0 is the probability that we have 2 good motherboards. In other words, none are defective. And that's an and probability because we're picking 2. So if I pick the first one, the probability it's not defective, well, if there's 3 defective, there must be 7 that are good, is 7 out of the total of 10. And then remember, our multiplication rule says now assume you took the first one, so that'd be 9 left. And what's probably the second one is also good, in other words, not defective. It'd be 42 out of 90. We'll worry about any simplification or anything later. All right, I'm going to save x equals 1. Let's look at x equals 2. This is probably both are bad, both are defective, because x is counting the number of defective motherboards. So probably the first one is defective is 3 out of 10. Probably the second one is now we've taken 1 out, so it's 2 out of 9. So this is 6 out of 90. Now, x equals 1 means 1 is defective and 1 is not. That could happen 2 ways. It could be the first one's bad or the second one's bad. In other words, it's complicated. However, I can use the idea that a probability distribution covers all possibilities. So my probability distribution is going to be x, probability of x, and it's going to be 0, 1, and 2. These have to add up to 1, or if you use decimals, they have to add up really close to 1. There might be rounding errors. So in other words, whatever these 2 add up to, since this is the last one remaining, this will be 1 minus that. So in other words, this is 1 minus 48 out of 90, because 42 plus 6 is 48. In other words, this is 42 out of 90. It has to be. Well, I did some quick calculations. 42 out of 90 is approximately 0.047. Or excuse me, 0.47. And so that's for x equals 0, x equals 1. And then 6 out of 90 is approximately 0.07. Now, if you double check this, it doesn't quite add up to 1. It's a little bit bigger, right? And the reason for this is because of the rounding. I rounded very heavily here. This is actually 0.4666 forever, 0.4666 forever, and 0.0666 forever. So I rounded so you end up with something a little bit different, not quite exact, right? I think you end up with 1.01 or something like that. That's okay. If you're rounding, it's understood that that could occur. So this right here ends up being my probability distribution. Well, another thing I could ask about associated with probability distributions is the expected value. And so the expected value here would essentially be the mean. It would be in the long run, if you were to repeat this experiment over and over again, how many defective motherboards would you expect to come across? And so in every time, so if you were to over again pick 2, on average, how many out of 2 would be defective? So expected value is the sum of each x times its probability. And so this would be, in this case, 0 times 0.47 plus 1 times 0.47 plus 2 times 0.07. And so this is essentially 0.47 plus 0.14, right? Which is equal to 0.61. So this is the expected value. This is the mean of the distribution. So it says on average, if you were to over and over again pick 2 motherboards, you would expect on average 0.61 to be defective. This is kind of like when you say, oh, the average household has 2.1 children, right? It's an average, so it's not always exactly a number you could actually have. The way a lot of people interpret this is you'd expect between 0 and 1, implying that most of your probability is around 0 and 1. This can be actually plotted very much like a histogram, and we could actually put x down here and the probability of x, and you'll see that this acts just like a mean. So if this was 0.5 right here, for 0, I'd be almost at 0.5. For 1, I'd be almost at 0.5. And then for 2, I'd be way down here. So you can see that this is somewhat skewed, if about as close as you can get to saying skewed with only 3 bars. And 0.61, notice, is about right here. So very similar to acting like a mean when you're looking at a histogram. But again, the probability distribution gives me a picture of everything going on. Expected value gives me what I would expect in the long run if the experiment is repeated over and over and over again.